All right, good evening, everyone. This is Robert Haynes here with the National Weather Service in Burlington. I have just about 6:29 on the clock here, but assuming a little bit of audio lag being present, I assume it'll start relatively close to 6:30 for you. Welcome to the Warm Season Spotter course. We've been doing a series of virtual courses over the last couple years, and we do these refreshers periodically. But if you are interested in joining the Skywarn Spotter Network for our local area, we'd be happy to have you. And we'll go over some of the what a Skywarn spotter is, what their purpose is, the role that they play with the National Weather Service. We'll talk a little bit about our hierarchy here, how we kind of play within the whole kind of build-up of where we sit in the government. And then, of course, we'll talk a little bit about what we do here at the National Weather Service in Burlington specifically. And then we'll start going into thunderstorm safety, a little bit of the science behind thunderstorms and some of the things that you can do to help understand a little bit more what you might see on radar, TV, or satellite, or just to give some general advice on how to best deal with thunderstorms in the safest way possible. All right, without any further ado, let's get started. All right, so for this presentation, we'll talk about what Skywarn is and the role that it serves. Again, we'll provide a little bit of an overview. We'll go over some of the different types of thunderstorms and convective warnings like the severe thunderstorm warning, tornado warning, things like that, and then as well safety. We will also mention, let's talk about what Skywarn is. It's a national network of volunteer weather spotters, and their reports range from all kinds of different weather phenomena. It can be from snow to flooding to thunderstorms, whether you see tornadoes or hail. The Skywarn Spotter Net is intended to take these observations, whether that be in your backyard or on the road, and send them over to the National Weather Service. The key distinguishing factor of a Skywarn spotter from any other person in the public is just that you've been trained by the National Weather Service for this role of observing these various weather phenomena. Skywarn originated in the late 1960s, early 1970s, and had its roots in amateur radio, with the idea being if communications like telephones were out, you could still relay information over radio, and that would be the way we would get our reports if those communication networks were down. But since then, it's expanded. It includes emergency managers, firefighters, law enforcement, local media, researchers, students, as well as other people in the general public. There are a few storm chasers that will join Skywarn Spotter Networks as well, and of course Co-op and CocoRa's, who also do a variety of other observation services for us here. The main idea is anyone can be a Skywarn spotter. How does one become a spotter? It's a completely voluntary network. So there's no kind of membership fee or anything. We just ask that you are trained by someone from the National Weather Service through any of the following means. Whether that be an in-person spotter talk or presentation. Sometimes we'll go out to schools, or sometimes local communities will come together asking for this kind of presentation. And if that's something that you're interested in, you can always let us know. We've also been offering virtual courses like the one you're participating in now, or through Comet MetEd. There is a training service that you can find on there, and that way you can kind of do that on your own time. If you happen to move outside of our area of responsibility, we do encourage you to contact that region's local National Weather Service if you'd like to become a part of their spotter network. We each as a different National Weather Service office take care of our local area. And upon that, we do ask for a physical location and a contact number, again, just to make sure that you are within our forecast area of responsibility. But also, there may be instances where we are seeking out ground truth observations, and we may contact you if we notice a storm moving into your area, and you can always let us know if that's something that you do not prefer. All right, so let's start getting into the meat of the presentation here. You'll notice on each of these slides I do have a slide number. If ever you have any questions, you can come back and refer to these slide numbers, and we can answer your questions most easily by being able to go back and look through the slides. There are also going to be a number of review questions, kind of going back to this idea of how does how to become a certified Skywarn spotter. Given that Facebook Live is it's difficult to kind of track who watches and what, I have a series of 10 review questions throughout the presentation. And if you email me, I'll have my email at the end of the presentation. Emailing me these 10 questions, I will consider sufficient evidence of attendance here tonight. All right, so let's get going on what a Skywarn spotter reports. The primary purpose is severe weather, whether that be funnel clouds or tornadoes, especially in our area where we have mountains blocking our radar beam. Also wind damage. Oftentimes wind damage in a local street may not always get reported to us. Skywarn Observer is often very helpful there, as well as hail, flooding, and of course in our area, snowfall. But it really can be just about anything. We do have a number of spotters who will, at the end of a day, after it's precipitated at all, give us how much rain or snow, if it happened to be snow, fell for that event. Ultimately, when dealing with Skywarn stuff, the level of involvement is entirely up to you. You can report as often or as little as you like. Just know that we do appreciate whatever information you do give us, but you're in no way obligated to give us any of this information. All voluntary. So why is it that we need spotters? Why do we kind of build this network of volunteer observers? We have all kinds of fancy technology, from our radar to satellite images to automatic weather observation stations to these radiosonde balloons that we send up in the atmosphere, and of course our weather models. We have all these different tools. So why do we need a spotter? Well, it's because they all have their limitations. They aren't going to be quite as good as the ground truth. For example, our radar beam gets blocked by the Green Mountains. So especially in the Northeast Kingdom, we aren't going to be able to observe anything generally below 4,000 feet because of both the mountains and because of the distance from the radar. It's not until we get closer to say 8,000 or 10,000 feet that we might not be able to see any of that precipitation. So radar might be looking high up in the clouds, but whether there's a wall cloud at say 2,000 feet above the ground level, we might not see that on radar, but a trained spotter can identify that, and based on the report, we can then adjust our warning based on that trained spotter. So really, spotters do play an important role across our forecast area, especially because a lot of our western areas along the St. Lawrence Valley and a lot of our eastern areas get blocked by our mountain ranges. This also comes in handy when we are talking about heavy snow. A couple years ago, we had a heavy snowfall event in March. We were thinking that, hey, it looks like a good chance for 1 inch an hour snowfall rates. We had, I think, somewhere between about 3 to 6 inches in the forecast. But one of our trained spotters called and said, hey, I'm seeing snowfall rates at 2 inches per hour, and I've already got about 6 inches of snow. And so we can adjust the forecast accordingly and adjust our warnings based on the phone calls of our spotters. So again, what radar and all of our fancy tools might tell us, really ultimately the ground truth from what our trained spotters report really goes a long way into helping us message our forecasts. And of course, your reports also help whenever we do summaries of events, especially when we have widespread severe weather or when we have high-end snowfall events. We will collect and gather all of your reports, and that'll help show the extent of snow, especially in areas where observation networks might be sparse, particularly the Adirondacks. This area of the world doesn't typically have as many reports as areas across Vermont. And so all of your photos help as well, and some of our spotters and some of our partners as well submitted some of the photos that we see here. So your reports go a long way into helping us understand impactful weather in our region. And briefly, since I also mentioned Co-op and CoCoRaHS, I'd like to just quickly explain here some of the differences between the three programs. Each of these are voluntary networks, but they each kind of entail something different. The Co-op or Cooperative Observer Network, they are a dedicated group of volunteers. They take weather observations daily, and this they do this over a course of many, many years, so they can have long-running daily climate reports. They manage the station records for that area and have very specific equipment requirements. And our observation program lead, Marlon, does a lot of that work. We rely on their reports daily, so it's a higher level of commitment, and sighting is critical. With CoCoRaHS, the primary focus is rain, snow, and hail, as opposed to all of the different temperature measurements. It's, again, a volunteer network, mostly people who are very eager to report weather on a daily basis. And the sighting is important, but it's not quite to the level of involvement that the co-op program is. And then, of course, the Skywarn Spotter Network is this volunteer network trained to focus on severe weather spotting, but also other weather phenomena. And the frequency of reports is as often as desired, and it can be wherever you are. You're not tied to a specific location when you're doing Skywarn spotting. All right, so let's start talking a little bit about who we are here at the National Weather Service in Burlington. We are part of these group of forecast offices across the United States, and there are some in the Pacific Islands, such as Guam and the American Samoa's Pago Pago. We have, between all of us, about 122 different forecast offices, and we each focus on the weather, water, and climate data and warnings to the protection of life and property, enhancement of the national economy, but specifically focusing on our local area. And our vision is to make a weather-ready nation, to make sure that our local area is prepared for and is able to properly respond to weather, water, and climate-dependent events. This training session here and this recording, this little educational session, is one of the ways in which we seek to make a weather-ready nation. So you get to be a part of our vision here tonight. The National Weather Service, we're a branch of the Department of Commerce. So we are technically a part of the U.S. government. We aren't a kind of business or private entity, but we're part of the National Oceanic Atmospheric Administration, and then finally we are kind of the front lines as far as what it comes to the weather in our local area. There's about 4,500 meteorologists across the National Weather Service alone, and this is kind of how it looks like when you have everything on a map. We each sit positioned within various regions. We're in Eastern Region, and of course there are various national centers, river forecast centers, and of course all of us here for our different offices. So specifically, we here at the National Weather Service in Burlington focus on the four northernmost counties of New York and much of Vermont, except for Bennington and Windham counties. We are bordered by the National Weather Service in Buffalo, the National Weather Service in Albany, and the National Weather Service in Gray in terms of forecasting. But again, we focus on mostly the four northernmost counties of New York and much of Vermont. And this is what life here looks like in our office. We have an open office concept here where we're all collaborating, understanding and kind of asking for each other's opinions and inputs on what we're seeing in the weather forecasts. We work closely together to make sure that we're making the best forecast, that we're not missing anything important or critical. We have all kinds of displays to help us see what's kind of going on in either the news or what's happening on with our local stations. We have all kinds of tools and technology, and we all kind of collaborate together. Definitely one of the best parts of being a meteorologist with the National Weather Service is we're not the only meteorologist. We have a group of people who enjoy discussing the weather together. Some fun facts about the National Weather Service. As previously mentioned, we're about 4,500 people, with about half of those being meteorologists. Our annual budget is approximately $1.2 billion as of fiscal year 2021. We're a very small portion. We don't even come up to 1/100% of the entire federal budget. Roughly, the taxpayer cost to fund the National Weather Service is roughly equivalent to a meal at McDonald's. Our farthest east office is San Juan, Puerto Rico. Farthest north is Barrow, Alaska. Down south, Pago Pago in American Samoa. And then farthest west, we have Guam. All right, So during these presentations, I'll have a series here where I'll look over at the comments section. If ever you have any questions during the presentation, this will be the time that I look over and see if you have any questions. So at this stage, are there any specific questions that anyone has about Skywarn that I can elaborate on? Or if you have any more questions about the National Weather Service in general, or if anything else is on your mind before we get into the meat of the presentation here. All right, I'm not seeing anything, and if you do have any questions or comments, I will come back to them when I look at the screen here at the next period for the next break for questions. All right, let's talk a little bit about safety. With this volunteer network of spotters, we have some storm chasers, but not ultimately too many. But when it comes to thunderstorms and hazardous weather, remember that your safety comes first. We never want you to put yourself in harm's way to get us any kind of weather report. Always stay weather aware, have multiple lines of communication out, have someone know where you're at who's able to kind of check in on you during severe weather. Have an escape route ready. If the weather turns bad, make sure you have a way to get towards your designated safety zones so that you can take shelter in the instance, say, a tornado happens. It's important to have a plan in place before severe weather strikes. Some of the best things that you can do to kind of summarize briefly the best things to do for each of these different severe weather hazards. In the instance of a tornado, it's best to take shelter immediately in a sturdy structure, ideally away from windows. If you aren't able to get to the lowest level possible, you want to try and get as much to the center of a building in a hallway without windows if possible. When dealing with large hail, of course, it's best to move indoors. Stay away from windows, especially if hail is particularly large. It may be able to break through the glass. Severe wind has much the same recommendation for your safety is to move indoors and away from windows should a tree fall on the building. And for flooding, avoid rising creeks and water-covered roads, especially we encourage you never to drive into flooded roadways, as that accounts for about 2/3 of flood-related deaths. And of course, for lightning, also move indoors if you hear thunder and stay away from any plugged electronics. For flash flooding, in these instances, you have very heavy rain causing rapid water rises in neighboring streets. You'll have to sometimes seek higher ground if necessary to get away from this flooding, but sometimes that can conflict with the need for, say, going to the lowest level possible if you need protection from a tornado. Always use your best judgment in these cases and understand some of the risks and hazards and have a backup plan if need be. It only takes about 6 inches of fast-moving water to knock over an adult and carry them away. It takes about 12 inches of fast-moving water to carry away a small car, and about 18 to 24 inches to move larger SUVs, vans, and trucks. Don't underestimate the power of running water, especially in these flash flood scenarios. It does not take very much to carry away people or cars. With lightning safety, of course, it's best to go indoors and not to go under places like a tree. Often when dealing with things like swimming pools, you want to kind of have 30 minutes in and 30 minutes out. If you can hear lightning within 30 minutes, best not to go out. Follow the 30-30 rule. It takes about 5 seconds for lightning, the sound of the thunder to travel 1 mile. So if you hear it, that tells you just roughly the distance of the lightning for your 30-minute rule there. All right, and of course for tornado safety, a couple other extra things to mention. Never seek refuge in a vehicle overpass. One, it's not going to protect you from the tornado at all, and it can also impede the flow of traffic. That can often cause traffic accidents that can sometimes be more problematic than the storm itself. Never seek shelter under an overpass, and it's also not recommended to seek shelter by trees in case they get uprooted. Then they become a source of they become a hazard for flying debris or anything like that as well. It's best to seek shelter indoors in a designated shelter, basement or a safe room, or again, any kind of windowless room if none of those are available. And of course, we are starting to move in the direction where heat safety is going to become increasingly important. Know the signs of heat exhaustion versus heat stroke, especially when you go from excessive sweating to a lack of sweating and have an increasing headache and body temperature. Those are your indications that you have heat stroke. Know the signs and seek shelter indoors in a cool air-conditioned place and hydrate before you have to make the call to 911 for any heat-related illnesses. When dealing with hot weather, make sure to slow down often. Avoid doing overly strenuous activities for long periods of time. Take frequent breaks and drink plenty of water. Seek air conditioning if necessary. And of course, if being exposed to the sun for long periods of time, always good to have sunscreen on hand. For our area, we issue heat advisories when the heat index is expected to be greater than 95 for at least 2 hours, and excessive heat warnings if the heat index is 105 or higher for at least 2 hours. So especially when dealing with excessive heat, that's especially when you want to be heeding this advice the most. Check up with friends and family, especially if they don't have air conditioning, and make sure they're well taken care of as we head towards the summer months. All right, let's hop into understanding a little bit about the science and behind thunderstorms and how we forecast them. When we're looking at all of our weather models or satellite observations or whatever we're looking at, when we're talking about thunderstorms, we're looking for 3 key things. We want to make sure that there's enough moisture. You're not going to get a cloud if it's too dry. We want to look for atmospheric instability. In other words, if you have any kind of cloud or pocket of air, is it going to keep moving up, or is it going to be blocked by some area where the atmosphere is maybe a little more stable? We also look for a forcing mechanism. Oftentimes, that's a warm front or a cold front. As we head into the summer months, we get warm fronts and cold fronts less often, but oftentimes the forcing mechanism isn't quite as important when you get into the summer months, as often the atmospheric instability can just do all of the legwork by itself in the summer months. To become severe, storms need a little something extra, and that's often wind shear. Wind shear helps thunderstorms organize and last a little bit longer than your standard thunderstorm. A variety of other factors can combine to make storms more or less organized, and generally the more organized, the greater the severe threat. And to put this into a map form, here's showing a cold front moving in from the west. We often get our moisture out of the Gulf of Mexico or from the Atlantic Ocean. And with ample daytime heating, we get all the ingredients right there to produce thunderstorms in our region. So we have all kinds of collaboration with the Storm Prediction Center. These people are set in Norman, Oklahoma, and they are the experts when it comes to understanding severe weather forecasting. And every single day, they produce these severe thunderstorm risk categories. And oftentimes, that's kind of our cue to take an extra look at what we're seeing here in our forecast when it comes to how we want to message severe weather safety and things like that. They use this scale here to describe the different the threat levels for severe weather for an area. You can think of it in 3 different ways. You can either look at the numbers, 1, 2, 3, 4, or 5, where the higher the number, the greater the severe threat. You can look at it based on the color, where the greens are less likely to be severe, where the reds and purples are to say that severe weather is likely, and it could be long-lived and intense, where these yellow and orange colors maybe kind of say more scattered, maybe not quite as long-lived. Or you can also think of it just based on the descriptor, whether it's marginal, slight, enhanced, moderate, or high. Whichever way works best for you to understand these severe weather categories. This just gives you an idea of whether severe weather is to be widespread or isolated, and each one kind of gets a little more persistent, more long-lived, and more intense as you go up the scale. So every single day, they create these maps contouring each of these different categories based on where they think severe weather is going to happen, with the aim of reports happening within a 25-mile radius of these points. And of course, they want most of the reports, ideally, when looking at verification, to be concentrated near where their highest threat level outlooks are. And so this is a mock-up of the super outbreak that happened April 27th in 2011. And so each of these risk categories are broken up into each of the different hazards for severe weather, and that would be wind, hail, and tornadoes. And so oftentimes they'll break it up into these different pieces, and then also try and provide an indication of whether or not the severe weather hazards in that area could reach significant levels. So for like tornadoes, for example, that would be things greater than an EF2. For winds, that would be winds greater than 75 miles an hour. For hail, that would be hail in excess of 2 inches in diameter for these hatched black contours here. And so this just kind of, all of these three components together come up to make their severe weather hazard categories. So hopefully that helps you understand a little bit about how they divide those out. And sometimes you'll see a lot of these repainted when you're looking at local broadcast media as well. They will often provide this information, but sometimes in a way that may be a little bit more digestible for the general public. All right, with that out, let's look at the severe thunderstorm watch versus the tornado watch. The severe thunderstorm watch indicates the potential for severe weather that's primarily going to be wind and severe hail. The tornado threat is going to be probably fairly low. That's not to say they can't happen, but tornadoes are not the primary concern when a severe thunderstorm watch is issued. When a tornado watch is issued, the tornado threat is going to be considered at least moderate. That's not to say that you can't have a very high likelihood of severe winds as well, but tornadoes are a likely factor when it comes to tornado watches. And so remember, this is to give an indication of potential. It may not necessarily play, but just the atmospheric conditions are at least pointing to a moderate threat for tornadoes. Of course, any other can happen, and they can also be of greater impact. Now remember, when we're talking about severe thunderstorm watches or tornado watches, we're talking about that weather conditions are favorable for severe weather development over the coming hours. It's to say that it might not immediately be there, but that's your time to be aware and to start thinking of having your escape routes, having your safety zones prepared if you need to. The warning is the severe weather is now imminent or ongoing, and that's when you take that escape route and safety zone. That's when you take your emergency plan and put it into action, and that's when you seek shelter, is when you receive the warning. A better way to think of that might be ingredients for baking. A cupcake watch might involve having your cream, vanilla, your flour, your sugar, your butter, your eggs all together prepared to make a cupcake. The ingredients are present, but the cupcake is not quite yet made. But when it's come out of the oven and you've layered on the frosting, you now have a cupcake warning. You're ready to enjoy your baked good. So that's just one analogy. You can also think of it, I've seen a lot of people recently refer to it as like a taco salad, a kind of thing where you have all your taco ingredients together. That indicates the watch. And then your taco warning is once your taco warning is made and all of your ingredients are put in a nice flour or corn tortilla. All right, so here's one of those previously mentioned review questions. If you are interested in becoming a certified Skywarn spotter, remember I'll be looking for these review questions in my email inbox. So the first question I have here, which ingredients are favorable for thunderstorms? Now I know again with the audio lag it might take a little while for your responses to reach the comments section here. So I'm just going to pause, delay just a little bit before I reveal the answer here. All right, our 3 ingredients that are favorable for thunderstorms are warm, moist air that helps to make for the convection. Almost like it's in an oven, you'll have air start to move up in the atmosphere, making your billowing cumulonimbus clouds. We're looking for air masses to move up, and when air masses move together at the ground, say with a cold front or a warm front, at ground level they have nowhere to go but up when 2 air masses meet each other. So that's your lifting mechanism. And then, of course, you want unstable atmospheric conditions. You want a storm to be able to continue to grow as opposed to being quashed by any kind of stable layer. And then, of course, I forgot to renumber these. That would be my mistake here. Question number 2. When the ingredients for tornadic weather are expected to come together for several hours, what does the National Weather Service issue? And that would be a tornado watch. When the ingredients are in place and tornadic storms are possible, the tornado watch is what's issued. Remember, it's to indicate that there's the potential that tornadic storms could occur. It's when the warning is issued that you take immediate action. All right, let's see if I have any questions here. Yes, I see the watch response. Correct for that for review question number 2/4. Exactly. A watch is what would be issued. All right. I'll look for any more additional questions. Next up, we'll be talking about the different kinds of thunderstorms. We'll get started in just a second there on the different kinds of thunderstorms. All right. I got ahead of myself. First, let's talk a little bit more about the warnings, specifically severe flash flood and tornado watches. So what is it when we say, hey, there's a severe thunderstorm warning out, and when you see it broadcast on the news, what all does that mean? When we're talking about a severe thunderstorm warning, we think based on radar indications in the storm environment that the potential for hail 1 inch in diameter or larger is possible within that thunderstorm, and significant wind damage or wind gusts greater than 58 miles per hour are possible. When it comes to a tornado warning, we see radar signatures or, of course, a spotter report of a funnel cloud, and that can be at any intensity for a tornado warning. Of course, we have different tags associated with different intensities of tornado. We've never seen anything higher than an EF2, but in general, tornado of any intensity for a tornado warning. And then, of course, for a flash flood warning, that's when we think that rapid rises in waters are possible that could affect urban areas or make fast-flowing waters or, quote, rivers of areas that shouldn't have water on them. Of course, lightning, though it is not a criteria for severe weather, it's important to know that it is a killer. We don't issue warnings based on the amount of lightning a storm is producing, but it is important to know sometimes we'll issue special weather statements if a storm is producing quite a bit of lightning but may not be reaching severe criteria. So some things you can kind of look at. Here's some of the common objects used to kind of describe hail. Typically when we're talking dimes or pennies, that'd be about 3/4 of an inch. The severe threshold is if hail is about the size of a quarter. A quarter is about 1 inch in diameter. As we start getting into the hen egg size, that's considered very significant hail. When you start getting 2 inches in diameter, this does much more damage to life and property here. Vermont's largest hailstone was about teacup size. Hopefully we'll never have to see the scale of grapefruits or softballs, as some states out west have to deal with sometimes. We don't always have too many ways to observe winds here. We have a ton of trees that can sometimes block observation sites from getting the most accurate wind gust measurement. But you can use some of these estimates to help kind of get an idea of what the wind speeds are. When larger branches are in motion and you start kind of hearing whistling in buildings and structures, especially kind of corridors and things like that, that's about 25 to 31 miles per hour. If your whole tree is starting to sway and it's becoming hard to walk in the wind, that's about 32 to 38 miles per hour. Usually it's about when you start getting 39 to 54 miles per hour that you start getting limbs and things off of trees. It's about 55 to 72 miles per hour that you start getting some more structure damage to chimneys, TV antennas, and even shallow trees can get uprooted. And then, of course, as you start getting to 73 to 112 mile an hour gusts, as you start kind of entering that hurricane force wind kind of area, you're starting to see roofs that can get peeled off. Windows might be able to get broken. Small mobile homes can get pushed. And as you start getting above 113 miles per hour, that's where you can start getting roofs torn off of houses, cars lifted off of the ground, and other more significant signs of damage taking place. But typically, we'll probably often most see our wind gusts in the 39 to 72 miles per hour out here. But occasionally, we will see storms that produce gusts likely in the 70 to 80 mile an hour category. The severe thunderstorm watch again indicates hail about 1 inch in diameter, wind gusts of 58 miles per hour or higher. But you might also notice occasionally we will mention a tornado is possible in the threat information. Sometimes we'll apply a tornado possible tag with our severe thunderstorm warnings whenever the signals are mixed or inconclusive. So if we can't get a clear image, say on radar, or if the rotation might not be particularly strong, we might indicate that a tornado is possible. Don't discount it, but the signals are mixed. The flash flood warning indicates the rapid water rises are happening or could happen in the warned area. We typically draw a wide net here just to account for potential downstream runoff impacts. And topography plays a large part in this, especially with our steep terrain. Several towns, I'll use Barrie as an example. Barrie sits at the basin of 3 different mountain areas where it all kind of converges in on the little town, and that makes that area of the world a common problem spot when it comes to flash flooding. When these are issued, never go near flooded roadways, just knowing that most fatalities are caused by people driving into or trying to walk past flooded areas. And of course, the tornado warning is issued when strong radar signals are present. This can be anything like a radar indicated rotation that's not just broad. Our fancy term here that we use, that we call it gate to gate, where we can see radar winds coming both in and out in close proximity, or evidence of lofting debris. Of course, a spotter report of a funnel cloud or tornado on the ground may also be the trigger for a tornado warning. In these instances, immediately seek shelter, and know that this could also include the threat of damaging winds and hail as well. All right, so let's look a little bit on the climatology of thunderstorms here in the North Country. This is specifically talking about our region here in Vermont and northern New York. Our severe weather season peaks in the summer months. Specifically, our most active severe weather month is usually July. And why is that so? We have more daytime heating in July, which lends itself to a bit more atmospheric instability. The Bermuda High is usually positioned such that we get moisture from the Gulf of Mexico advancing well northward into our area. Think about those days when we have dew points in the mid to upper 60s in the middle of July. We can often thank the Bermuda High for that. And then also in the summer months, we still can get fronts from time to time. Areas like Florida often don't get fronts in the summer season, but we can occasionally get weak frontal boundaries that do help thunderstorms develop. You'll notice here that hail takes a little bit larger of the slice of pie here on the line of the bar chart here in May and June, whereas many more wind observations happen in July. Some of that, the early spring season, the area where the temperatures are below freezing in the atmosphere are still a little bit lower than, say, in July. The freezing level in May and June might be about 5,000 to 10,000 feet above ground level, whereas in July sometimes it can get as high as 15,000 to 20,000 feet before you get below freezing in the atmosphere. And then, of course, as we head into the fall months, our severe weather season comes to an end as we start losing our daytime heating. Breaking it up into each of the different hazards. Wind reports, we get wind reports almost any time of day, but they are focused primarily between about 1 p.m. and 10 p.m., again, because we rely a lot on daytime heating to be able to help thunderstorms develop. As far as hail is concerned, you'll often see the same trend. The highest number of reports here, where we get, say, 40 to 80 in our record from 1955 to 2016. Most of the hail reports in our period of record occurs in the middle of the afternoon. And with tornadoes, sometimes we don't get as many reports at night because people are asleep during that time of day. But again, the general focus being between about 1 p.m. and 10 p.m. for our severe weather in this region. And now if we were to look at it in a map, you'll notice that the concentrations of severe weather reports is typically going to be in these areas where there's at least some kind of population. We're looking at areas like towns like Burlington, as you head towards Barre, Montpelier, Rutland, and you'll notice a lot less in the Adirondacks and far fewer in the remote stretches of the Northeast Kingdom. So typically roadways and population centers, you're going to see a higher concentration of reports as people are able to have hail being hit on their car or their window. Typically hail is going to be following those networks. And with wind damage, it's going to be more focused along urban structures where buildings might be more impacted, power lines and utilities are going to be more impacted. But sometimes you'll get wind reports out on the hiking trails as well. And then, of course, with tornadoes, it's largely terrain influenced. There's no really noticeable correlation to population centers, but the north-south orientation, especially of the Champlain Valley, and as you head down towards like the Hudson River Valley, the north-south orientation is important. Winds will like to come in from the south across these, funneled between the Adirondacks and the Greens, where winds aloft might be more westerly, and so the channeling of winds can kind of help a little bit of that storm rotation as storms kind of move into the eastern Champlain Valley. Oftentimes we'll get quick little spin-ups here, but oftentimes steep terrain, the variation in slope, it impacts the wind the circulation of a tornado. So typically it's less favorable once you head towards like the higher terrains. And then, of course, as you get to some of the localized valleys, in say near Newport, or sometimes in the Connecticut River Valley, and sometimes stretching close to Montpelier. You can get another small area here. So really our hills do a lot to prevent tornadoes across our area. The strongest you'll see here on the map are EF2s, and not many really track for very long on this scale, but mostly EF2s, EF0s or EF1s in our area. All right, that does it for talking about convective warnings and the severe weather climatology for our area. Let's see if I have any questions in the inbox at the moment. All right, not seeing anything at the moment. Let's do some of our more of our review questions here for those interested in being Skywarn certified. All right, so here's question number, well, I think it's at 3 at this stage, but again, forgot to renumber these. But as storms develop and radar indicates strong concentrated rotation, what does the National Weather Service issue? All right. If you set a tornado warning, you are correct. That is what we will issue if we notice the radar indicates strong rotation or even lofted debris. However, note we might also elect to issue a severe thunderstorm warning with a tornado possible tag. So it's also possible we might issue a severe thunderstorm warning just in case one or other signal is mixed. Let's say the strong rotation is happening at, say, 10,000 feet above ground level. It's just to suggest a greater degree of uncertainty that a tornado is reaching the ground. Just note it's a possibility. But in general, strong rotation, strong radar image, that is going to be a tornado warning. Which month climatologically sees the most active weather in the North Country? All right, and if you said July, then you'd be correct. July is our busiest severe weather month here in the North Country. All right, we're now at the stage where we're going to talk a little bit about the different kinds of thunderstorms. Storms come in all kinds of different shapes and sizes. They can be more or less organized, and we'll break up each of the different kinds of thunderstorms and the threats and hazards that you can expect from it. Oftentimes when we're discussing what we expect from convection for the day, we'll say, oh, mostly single cell storms today, or maybe some of these other storm types you'll discuss. Sometimes you'll hear us use this language, and this is what we mean when we say these things. The single cell is often referred to as popcorn thunderstorms. These are small and brief. They're rarely severe, and they're mostly driven by afternoon heating in a conditionally unstable environment. These storms can produce brief heavy rain as well as clusters of lightning strikes. And so this is how a single cell develops, or rather this is what it looks like on radar. The single cell is going to be mostly off on its own. It's not going to be near any other signals on radar. It's not associated with any big weather system. It's just generated by the heat of the day. It forms as adequate heating allows the parcel of air to move up to the higher parts of the atmosphere. The updraft is strong enough that water droplets or ice crystals begin to coalesce, and as they become heavier or move outside of the updraft area, it'll start to rain out. The single cell naturally brings its own demise by raining out as the downward motion of cool air out of the thunderstorm in the rain starts to descend. It effectively removes the updraft from the storm, and the storm begins to dissipate. And so you'll sometimes see it almost kind of cut out from beneath itself as you see this happening. Now, if a single cell is to be severe, when you're out looking for the potential for severe thunderstorms in your area, the best thing to look for is the overshooting top, or sometimes we'll call it the anvil cloud. And this is to indicate that in particular this storm is producing a vigorous updraft and is most likely to produce damaging winds through downburst winds. So especially if you look for these clouds kind of fanning out from the top of the thunderstorm. That's your anvil cloud and your sign that this storm might be a little bit stronger than your average storm. And so this is kind of what a downburst might look like on radar. We were looking for pure divergence in the radar returns. So in this instance, we see radar showing winds moving towards the radar at 60 knots, but just a few miles away, we see the radar indicating winds moving away from the radar at 40 knots, just right next to each other. So when we see this divergent signature, we know that the downburst has taken place in a thunderstorm at that instance. If we haven't warned on it, we might be a little too late at this stage. So sometimes we try and look for it, the signature of the downburst kind of happening if we can before it reaches the ground. But especially when you're talking about an area where the radar might be missing the lowest 10,000 feet, we might not always see those. An extreme example of what a downburst wind will look like, it'll essentially flatten the trees, kind of fanning out from where the downburst hits the ground. So essentially as kind of the opposite, when you have converging air at the ground, it has nowhere to go but up. But on the other side of the spectrum, if air is kind of moving down towards the ground, it then has nowhere to move but out. And so it causes trees in these extreme cases to be toppled over like so. Don't see too much like this every day here. Usually it does damage to just breaks off tree limbs or sometimes uproots them. Rarely will we see something like this. This is a bit of an extreme example. Just again, get the picture. Now a little bit more organized are the multicells, or sometimes we'll call them pulse thunderstorms. They're a little bit more organized and they're very common during the summer months. They typically form kind of as single cells start to merge together throughout the day. And with a little bit of more organization, they often create almost miniature cold fronts in and of themselves, or they're called gust fronts. These type of storms can be, they're more likely to be severe, capable of producing strong winds, hail, and there's a low chance. It's pretty conditional for these type of storms to produce tornadoes. Really, when we're looking at multicell or pulse thunderstorms, we're most concerned about flooding, especially if they're slow moving or if they happen to move over the same areas over and over again. And what they look like on radar, you'll see that now high reflectivities on radar are clustered together, almost kind of like a blob. Not really any kind of strong organization signatures, but you can sometimes see on radar the gust front evident. Essentially, as winds move out from the thunderstorm, they kick up bugs and dust and other kinds of debris in the air. And sometimes the radar can pick those up. And that can be an area where new thunderstorms might initiate down the road. Now, on the higher scale of that, a little more organized is the squall line. The fancy term is the quasi-linear convective system. Essentially, the squall line is just trying to communicate the high wind threat. With these kind of thunderstorms, high winds are very likely straight line winds, sometimes as they'll be called. There'll be a group of thunderstorms organized almost in a neat line on the radar, and they're accompanied by high winds and heavy rain for a very brief moment of time. But then because they're more north-south oriented, especially if they're moving fast east to west, it might be bam, just 30 minutes and then you're done. And so these are a little less prone to tornadoes, just due to the straight line winds. There's not often a whole lot of turning, but occasionally, in the right environment, you can sometimes get areas where the line bows, or where sometimes there's a little bit of rotation out ahead of it that can produce short-lived tornadoes, sometimes on the leading edge, or sometimes where you have little notches or any breaks in your squall line. So this is a little more higher up on the organization scale. And of course, how does this kind of take place? As you develop a cold pool in your thunderstorm, you still have winds aloft kind of pushing the storms off to the east, and you get what we sometimes call a rear inflow jet. So as as your strong radar returns are kind of fanning out, you have strong winds coming in on the backside, kind of helping to bow it out a little bit. That's often an indication. We'll look for bowing segments, sometimes we'll say, when we're talking about damaging winds. So strong winds aloft getting mixed down into the surface right on the back side of these thunderstorms, along where the cold pool is taking place. And on radar, we can see this oftentimes by sharp reflectivity gradients, where we get a lot of these reds and oranges right next to these very light blues. And of course, radar can pick this up with strong outbound velocity signals. You can see an enhancement of the color there. Or sometimes you'll see the strong winds on the backside of the reflectivity, or these weak echo channels. This would be their instance of your rear inflow jet. And these are both good indicators of whether you have a microburst on your hand or you have strong winds mixing down to the surface. And of course, it's a reminder that it doesn't take a tornado to produce significant wind damage. These are just some instances of what wind damage is capable in a microburst. This happened in Waitsfield in 2018. Some of our survey photos that we took showing the peeled roofs, flattened barns and sheds, and snap trees in this particularly strong downburst that took place in Waitsfield. And of course, multi-cell clusters can organize themselves into squall lines in the right environment as well. One of the more recent examples being May 4th of 2018, where we had a series of multi-cells organized into a squall line that produced widespread wind damage across Vermont and northern New York. We'll let the loop play again. You can see storms beginning to develop across New York, begin to organize. And as you approach the Champlain Valley, you have more storms kind of lining up here together, and ultimately producing a line where you can see a little bows here. Those would be where the strongest winds took place in this event. This would probably be, out of the last 5 years, one of the more significant severe events in the area was this event here. Let's talk a little bit about shelf clouds here versus wall clouds. Shelf clouds are going to be your number one signal that you have a squall line approaching. Often squalls are going to be accompanied by these shelves or roll clouds. Oftentimes as you have the cold downdraft ahead of the frontal boundary, but then you have warm inflow. It creates a little bit of turbulence out ahead of the precipitation that gets this nice structure that develops out ahead of it. So if you see these long, wide expanses of this shelf cloud, you're in probably for very heavy rain at the very least, and possibly some damaging winds. And so you can see, like here, no rain falling, very visible skies, heavy rain falling, less visibility. So it can often create this nice little border here between nothing and very heavy cats and dogs kind of rainfall. And an example here more recently from our area of an approaching shelf cloud here, a panoramic shot on the rooftop of the Burlington airport. See an incoming shelf cloud here, a wide horizontal expanse of clouds moving towards the area. To differentiate it from a wall cloud, again, you kind of want to consider the horizontal expanse of a shelf cloud is going to be much larger than a wall cloud. And then a wall cloud is also going to be rotating. With this, you're looking for an isolated area of the cloud where the base of it is notably lowering. Whereas a shelf cloud is going to move out ahead of your gust front and going to be formed together by the inflow of the storm itself, or the inflow of winds into the storms as well. And then if we were to take this further to the extreme, we're talking about derechos. These are lines of intense, widespread, fast-moving storms. These are going to be most favored in the summertime months, and they develop as a result of extreme instability. And with just the right atmospheric conditions, they can continue going on overnight. They form these little vortices where sometimes you can get these red dots, which would be tornado reports, but most often you're going to get an area of extreme winds. The criteria, I can't remember it off the top of my head, but generally widespread hurricane force wind gusts happen in derechos. They can also produce tornadoes, but really the winds are going to be the most significant part of this. The main difference with this is just the aerial coverage of wind. That's the main designating factor of what makes a derecho is how big was your wind damage. And this one did millions of acres of damage to the Adirondacks, as well as to the other forests across New York and Massachusetts especially. And you'll note the time of day, this happened overnight, and so this caught many campers off guard as well. This was a particularly dangerous one that happened in July 14th and 15th of 1995. Again, we always look at July as being our month to watch. Fortunately, though, derechos are very uncommon across this region. Climatologically speaking, about 1 in every 4 years, and I think even more recent research has been calling even this number into question. It may be a little less frequent as well. They're not a common occurrence up here, but they can happen from time to time in extreme cases. What this looks like on radar, it looks a lot like the squall line. Often the defining characteristic here will be this little notch here, the bookend vortex at the top of where this line of thunderstorms develops. So this is from Albany's radar here, showing the advance of this strong radar. And some of these, not these specifically, but this signature here, that might just be debris being kicked up by some of the strong winds as these storms are moving southeastwards. And then finally, we've talked a lot about all kinds of different storms. Last but not least, the supercell. These are highly organized storms that feed on strong updrafts, and the key defining characteristic of the supercell is that they are tilted and rotating. This feature of a rotating thunderstorm, when we see that, we'll call it a mesocyclone. So essentially, that's just another way of saying small cyclone. Whereas when we're talking about large areas of low pressures, we just sometimes generally call those cyclones. So when we see a small thunderstorm rotating, that feature, we'll call it a mesocyclone. Oftentimes this will show itself on radar, not every time, but classically we'll see the hook echo as rain from the downdraft wraps around, and you'll have southerly flow here rotating in, and it kind of gets pulled to the west, and some will get fanned out to the east as you get a little bit more upper diffluence. So you get this area here where we call it the V notch here. And so this is going to be where your hail is going to be taking place, as well as your very heavy rainfall, where your tornado is going to be more where the downdraft and the inflow into the thunderstorm kind of interface. And so occasionally you'll see a debris ball out ahead of the hook, and that's to indicate lofted debris. It might not actually be precipitating there, but things like leaves and trees and especially in wheat fields, it'll pick up chaff, and that's very reflective to the radar. So sometimes you'll see these lofted debris balls, and that's an indication that a tornado is on the ground. These supercells are very tall due to their vigorous updrafts, with storm tops exceeding 50,000 feet into the atmosphere, which means they often go higher beyond the troposphere and go a little bit into the stratosphere. These are the most likely type of storms to produce a tornado, but even then it's only about every 1 in 5 that produce tornadoes. So even with a supercell, about 20% will end up producing a tornado in its life cycle. Now, with these, very large hail is most likely due to how wind shear the storms tilt, and its rotation helps to keep the updraft of the storm separate from the downdraft of the thunderstorm. It helps them to be a little bit more persistent, and as a storm lasts longer, as you have water coming in and out of a layer that's above or below freezing, that makes it very likely to produce hail. Supercells are going to be prolific hail producers. And that's what that's more often than not what we're going to be most concerned of when we see supercells forming. With the fact that hail is most important in a supercell, let's talk a little bit about hail formation. So at some point, as you go higher and higher up into the atmosphere, you will reach the freezing point, and any water droplets will start to freeze and become hailstones. And so as it begins to fall, it'll start melting on its way back down to the ground at least a little bit. But in the case of a supercell, again, where your updraft and downdraft might not be co-located, sometimes, especially in very strong updrafts, some of those hailstones can be picked back up, collect a little bit of water droplets, and move back up where it's below freezing and grow a little bit larger and larger. So sometimes hail will cycle in and out of this, melting and refreezing, sometimes before it makes it down to the surface. If ever you get the opportunity, you can cut the hailstone open and you can see each of the rings from the times that it moves in and out of the area of I guess the column where it's above or below freezing. So even supercells can produce hail even in the most unlikely of scenarios. It might not be the ideal storm environment, say in Messina, New York, and in a relatively cool day on October 1st. It was only about 60 degrees, hardly what we look for when we're talking about strong thunderstorms, but it managed to produce 2-inch hail. Just because of the fact that with a supercell you get a better separation of the updraft and downdraft that helps hail to circulate and grow. What does hail look like on radar? Hail is going to scatter the radar beam differently than liquid water. So you'll see this artifact because it reflects differently than rain. And we'll commonly call this well, maybe not commonly. The fancy term, I guess you can say for it, is the 3-body scatter spike, or simply the hail spike. And when we see this signature, that's a good indicator that you're probably dealing with severe hail. Vermont's record hailstone is 3.25 inches. This actually fell in one of our employees' backyards. When we talk about measuring hailstones, you measure tip to tip, no matter how amorphous, how chaotic, how irregular, blob-shaped it is. Measure from tip to tip as best as you can and do it fast, because that hailstone is melting. If you do happen to get record hail in your area, sorry if you do, but try and take a photo to back up that, because it's not every day that you get 3.25-inch hailstones here in the North Country. And then finally, the tropical cyclone. These are concentrated areas of thunderstorms that develop over warm ocean waters. The process of convection results in a very special kind of microphysical process that helps get these going. It results in an area of falling pressures, and as it becomes more organized and more convectively driven, you start to develop these hurricanes, as we call them specifically here for this image on the left, of a highly organized area of convection that forms almost these kind of ring structures where you have the updrafts and the downdrafts of convection, and then you have a central focus where the eye wall takes place, where the most intense convection is organized. And what that looks like on radar, you can see bands of very high reflectivities across the radar with some pockets of lower reflectivities where there's some of those breaks in the convective band structures that you get. And then, of course, of satellite, the signature donut hole, the eye of the hurricane, in particularly organized systems can be seen. Now, with hurricanes, of course, these are really, really driven by the warm ocean, that special microphysical process, latent heating, we call it. So once it moves over land, it loses that warm ocean water, and that greater friction interrupts the specific circulation that helps that gives it that convective structure that helps lower its pressures. So once it moves over land, it quickly decays. Nevertheless, you still have to deal with the hazard of very efficient rainfall processes. There's going to be small drops, but because there's small drops, they can come in greater volume. They can be quite numerous in count and produce very high rainfall rates. Flooding is the most common thing. Situationally, tornadoes are possible, and of course, sustained wind damage is also possible when dealing with tropical cyclones. All right, so that describes each of the different kinds of thunderstorms. We've talked about the lonely single cell, the popcorn thunderstorm, and we've gone up an organizational level to the squall line, to the supercell, and even to the tropical cyclone. We've talked a lot about some of the. There's some deeper science here. We've glossed over it, but just to give you a little bit of a understanding of how and why, and maybe some of that. For some people, I know that helps them kind of conceptualize and kind of make a picture in their head. Maybe that helps you plan and make the best, take the best course for any severe weather hazard, and that might give you an understanding if you're interested in storm chasing. But with that, any questions before I move on to the review? All right, not seeing anything at present. All right, so what is it that distinguishes a supercell from the average thunderstorm? If you said that they are rotating or the updraft is tilted, that would also be acceptable. That is correct. The key difference between a supercell and any other thunderstorm is that it's rotating. While supercells are associated with tornadoes, remember only 20% of supercells will end up producing a tornado. So a tornado is not the distinguishing factor with a supercell. Remember, it's all about rotation. All right, next question. The National Weather Service is the only entity that issues official watches and warnings for the United States. If you said this statement is true, you'd be correct. We are part of the Department of Commerce, and our warnings and our warning products are intended to protect life, property, and enhance the national economy. So our products are mainly made to protect life. However, if you are interested in, say, specific weather phenomena as part of a business organization or structure, and you want different weather criteria, there are different organizations and businesses that can help you with that. But as far as official watch and warning products, it's all us here at the National Weather Service. Excellent. I see some correct answers here. Hopefully I'm giving enough time with the audio lag there. You can always let me know if it's not quite enough time. All right, and the next not another question here, but we're into the tornado segment of our conversation here tonight. So let's talk a little bit about what tornadoes are and what not to look for with a tornado. Specifically, a tornado is a violently rotating column of air that's in contact with the ground. Climatologically, they're very rare here, about 1 in every 2 years for our area of Vermont and northern New York. There are a lot of tornado lookalikes out there. They're called scud or convective debris. When we're analyzing tornadoes, or think, hey, that might be a tornado, ask yourself some of these questions. This can help kind of separate the fields of a trained weather spotter versus a person from the general public here. And this is challenging stuff. It's not easy. Ask yourself these questions. Is it attached to the cloud? Might you be mistaking it for a rain shaft for a cloud? That's also possible. So think, is it moving up into the cloud or is it rotating? If the answer is no, you're probably not dealing with a funnel cloud or a tornado. So this is an example of convective debris that we got on one occasion. It kind of almost looks like a funnel cloud, just the way it's roped. But radar indications showed that this storm was not rotating. So we ruled that this was likely convective debris. And then, of course, this is what a rain shaft might look like. Sometimes the sun can hit it just right, and remember, as the rain shaft is moving down, you get the air flowing out. But sometimes you'll get sometimes some neat images where the rain kind of curls a little bit into a little bit of a turbulent eddy, and so sometimes you get a little bit of a swirl, and sometimes that can get more mistaken for a funnel cloud. So ask yourself if this is part of the rain shaft as well. It can be tricky to determine. So if asking us to evaluate, just remember it's really helpful to have a video. It's hard to answer without being able to see whether or not it's rotating, whether it's descending from the cloud base. And of course, when you send us these photos and your videos, also make sure to give us a timestamp. That way we can match it to whatever we're seeing on radar. And then, of course, let's distinguish the funnel cloud from the tornado. Remember, it must be rotating. A funnel cloud specifically is not going to be touching the ground, whereas a tornado, it is going to be in contact with the ground. Now, in our area, sometimes the tree line makes that really challenging to determine. That can sometimes be mitigated by trying to see if you have any debris that's being lofted up. That can sometimes be a helpful way to determine whether it's in contact with the ground or not when you're dealing with a pesky tree line. Now, each of the designations, weak tornadoes, EF0s and EF1s, comprise 80% of all tornadoes in our database. Of course, these numbers are a little old. I haven't seen maybe some of the new numbers yet. They're probably out there, but I might need to do some hunting. I imagine it's roughly still accurate to today. 80% of tornadoes are going to be weak, EF0 or EF1, and they account for less than 5% of tornado deaths. Their lifespan tends to be short-lived, about 1 to 15 minutes with a path of up to 3 miles. EF0s to EF1s will produce winds of about 65 miles per hour to 109 miles per hour, and most of our tornadoes are going to fall in this category. Strong tornadoes, which would be EF2s or EF3s, account for about 19% of all tornadoes, and in less than 30% of tornado deaths. Their lifespan is going to be a little longer due to the more favorable environment, and typically are a little bit more longer in their tracks, with about 15 miles as their typical path length. Their wind speed is going to be anywhere between about 110 to 167 miles per hour. So at this point, you're capable of taking off roofs at this stage or moving mobile homes. And the violent tornado, hopefully we'll never see those here. They account only for 1% of all tornadoes, but 70% of tornado deaths. Unfortunately, they also tend to last the longest and have the longest path, being about 1 hour long in lifetime and about 50 miles in length for their path. Wind speeds here are about 168 to 234 miles per hour. This is enough to completely level structures. Sometimes even your sturdy interior is not going to be sufficient to protect you in the most violent of tornadoes. All right, that's a brief overview of tornadoes. With that, I'll look over for any of these questions here. And I do see a mention of the tornado last year in Middlebury. If we have a little bit of time left over, I have a few bonus slides on the Middlebury tornado that we'll go over. I've seen aggressive dust devils in the southwest desert. Why are they not F0 tornadoes? That's an excellent question, and one that honestly I can't think of off the top of my head. I know there are some instances where you'll see land spouts or water spouts, and they are formed a little bit differently from your standard funnel cloud. Whereas like a funnel cloud, ideally, you're talking about a descending cloud base touching the ground. But oftentimes with land spouts and things like that, they're moving up into the thunderstorm. They're kind of at the early stages of thunderstorm development. They're kind of hard to detect. With dust devils, I don't know if they kind of, again, part of me, this is me speaking out of my lack of experience, not having ever lived out west. I don't know if they kind of push those into their haboobs or anything like that. Audio lost. Oh dear. Oop. Test. All right, looks like I have audio now. Apologies for the lost audio there. So, to reiterate, I'm not 100% sure on the. Oh no, is it back? Did that solve the audio issue? I'm getting some mixed signals. Okay, excellent. I see we're all good then. All right, so just to reiterate, I'm not 100% sure on why dust devils specifically are marked out, are not marked as a part of the F0. I'd have to dig a little deeper into that. I'm sure they have a fairly good reason. I know in some instances also on fires, I know sometimes they'll make special exceptions for that, just for the special. I mean, sometimes you'll see us message things specifically with our warnings, just to kind of convey the sense of emergency. Tornado warnings are something that get people going, and that's the intention. We want to make sure that the messaging of that sets people to take the appropriate actions to take safety. And so it may be just with a dust devil, it might not be quite enough. It may be difficult, just again, dust devils being very low to the ground. A radar might not be able to adequately pick that up to be able to warn for them. So not 100% sure, but I'd have to look into the reason for it. I'll get back to you on that. Once we finish the meeting, I'll see if I can find an answer for you. All right, so here's some of the review questions here. Where is the safest place to be in a thunderstorm? And the answer for that is inside of a building, away from windows, and ideally in a central room. Not under a tree. There are definitely videos out there of trees being struck by lightning and then splintering from the force of the lightning strike. All right. So next up, we'll talk briefly about flood warnings versus flood watches and flash floods. This can be sometimes some of the more confusing aspects of our warnings here, but they often are the most impactful to life and property. So let's spend a little bit of time understanding flood warnings and flood watches. Again, the watch is to indicate that the ingredients are kind of there and the conditions are possible, whereas the warning is to indicate it's imminent, it's happening, or will happen very soon, and that's your time to take action to seek higher ground, and of course to avoid flooded roadways. Oops. So I have two videos here to kind of show some of the differences between flash floods versus floods. Ideally, a flash flood, or just kind of conceptually, the two are different because a flash flood is going to occur from excessive rain happening in a very short window of time. Sometimes they can transition into aerial or river floods, but a flash flood it's fast. It happens and then it's done. So oftentimes excessive rainfall is going to cause that. Sometimes it might be from something that's not necessarily from a thunderstorm. Sometimes a flash flood might be associated with, say, ice jams. Of course, again, ice jam flooding can transition into a regular flood as well. A flood is all about gradual rises and contributions, a longer span of time between those. So we'll just start playing these videos to kind of show here some of the differences between a flood versus a flash flood. Again, a very sudden change here on the left versus here the image right from the Vermont Agency of Transportation. This happened in April of 2019. This is the White River being flooded by gradual contributions from heavy rain and snow melt here. And then, of course, this is the Ausable River ice jam that happened in 2018. You can see the very sudden rise that happened there as water rapidly entered the region, and as the jam flooded out, eventually the waters were able to recede. So there's just to kind of show the difference between a flood and a flash flood. This is a map for flash floods, but in general, the flood season is most common at the same kind of time frame for the most part. Snowmelt is the greatest contributing factor during the early part of the year, in March and April especially. As you head towards June, July, and August, that's thunderstorm season. So thunderstorms do a large part of flash flooding for the summer months. And then as you head into towards November, you actually start getting vegetation that's becoming dormant. So as a result, vegetation isn't collecting all of that water, and so more of that tends to run off as opposed to being soaked up. So those are the three time periods where we most commonly see flash flooding. It can happen at any time of year with the correct atmospheric pattern. Anything that brings strong moisture laden storms, especially if they're going to be interacting with any tropical cyclone, or if it's a recurving tropical cyclone, any of these factors that can bring large amounts of moisture are going to have that potential for flash flooding. And of course, it's all just remember to not underestimate the power of flooding. You'll see there's some non-convective hazards, but as far as like severe kind of stuff like lightning, tornadoes, and wind issues, you'll see that flooding takes the cake compared to all of those. And then if you consider that across the rest of the span of all weather-related hazards, you'll see that in 2019, specifically, it was in 2019 specifically in the red bar here, it was number 1. But even across these multi-year averages in blue and yellow, it at least took number 2. So flooding is particularly a much larger weather hazard than many of our other things, and we encourage you to take flooding probably the most seriously out of all of our different warning products. In the event of rising waters, seek higher ground, and of course, sometimes note that you may have to leave an interior structure. Use your best judgment and stay calm. Best not to be caught unawares, whether that be from spring flooding or from ice jam flooding. Make sure that you are prepared to take actions when flooding happens. And of course, never underestimate the power of running water, because you might not be able to see if the road is intact beneath floodwaters, especially at night. It's impossible to see what's happening underneath the road. Heed all road closures. You never know if there is a washed out culvert and you might drive into it. So turn around, don't drown. Avoid floodwaters wherever you can. So that's a very brief overview of the flood segment here. I'll look over for any additional questions here. All right, not seeing any at present. And so with that, we move on to our next review questions. I guess I've already given you the answer here for number 8. What makes a flash flood a flash flood? And so that's going to be sharp, sudden rises in waterways. These are going to be caused generally by excessive rain and water runoff that makes rivers out of roadways. It's short-lived. It happens in a flash, and then it's gone. All right, so how much, calling back to earlier in the presentation, how much moving water does it take to sweep away an adult? If you said 6 inches, you are correct. That is how much water it takes, as little as 6 inches to carry away an adult. All right, we are moving into the recreation season of the year. So let's talk a little bit about Lake Champlain and forecasting the winds over Lake Champlain. With the water, it's really it's a different world almost. You don't have any trees or buildings or mountains. You just have a flat expanse of water. So there's not as much friction over the water. And so as a result, your winds are probably going to be stronger than what it is on land. But the temperature profile of the atmosphere plays a large part. If your water is warm and the air is cold, then you're going to be very unstable and able to mix strong winds down to the surface. Whereas if your lake is cold and your air is warm, then it's going to be a little bit more stable. And then, of course, we have the additional consideration of channeled flow in the Champlain Valley, where winds will accelerate between us and the Adirondack mountain range. So just to break it up by season, the winter months, remember with water, it heats and cools much slower than air. So it takes a long time for the lake to get really cold in the winter months and to freeze over. It usually doesn't freeze over until February or March. So say in the winter you have cool sea surface temperatures, but you have the Arctic blast coming through. So the air temperatures are very cold. It's going to be unstable. There will be strong winds on the lake. During the spring months, now you're kind of heading into March and April. At this stage of year, I didn't check what the lake temperatures were today, but when I checked a few days ago, it was still only in the mid-30s. So as a result, the lake is relatively cold, but now we're having several days where we're sitting in the 50s and the 60s. So as a result, the lake is relatively stable at this time of year. During the summer months, we're still waiting for the lake to reach the peak heating. The lake doesn't usually finish heating until September, so the lake might be 60 or 70, and the air temperature is now in the 80s and 90s, so still stable. As we start transitioning into September and October, now it's taking the lake a very long time to cool off, so the lake is relatively warm, and we're starting to get cold air masses back in. So back in the fall, we start getting more unstable and strong winds. And so here's just to break that out by chart. This is the frequency that we see strong winds of greater than 25 knots on Colchester Reef. Have each of the months outlined here, and of course each of the seasons broken up. Summer months, a lot less common. And of course, as you head towards fall, you see a gradual rise from September, becoming more and more frequent, peaking around December and January, and then falling off as you start heading back into February, March. Generally most quiet lake conditions, June and July. This is a wind rose, which is to show which direction the wind most commonly comes from. Each ring kind of represents a percentage. So the longer it is, the more frequent it is. So with this, a south and a south-southwest wind are most common, whereas you can also get a north or a northwest wind. You'll see that pure east or west winds are very hard or uncommon on Lake Champlain because of the channeled flow of our valley. Specifically, we have the Adirondacks on the west and the Greens on the east. So winds are going to be funneled between them, resulting in what you see here with the mainly north and south component to winds on Lake Champlain. So that's just to get you a quick overview of how winds work on the lake. So at this point, we are moving towards the end of our presentation here. So I want to have a few reminders here as we begin to start getting towards the end of our time here. An effective spotter is going to answer these questions when offering reports. Where are you located? What was the severe weather? And what time did it take place? Remember, we need to match it to radar. And sometimes it's good to know how long did it last. And of course, it's also important to remind us of who you are. We all work rotating shifts. It's not going to be the same person day in, day out. So we might not necessarily know you're in our spotter network. So it's sometimes good to say, hey, I'm so-and-so, and I'm part of your spotter network. That gives us a little bit more of a clue of where you might be at and what you are doing. So again, we want to be able to also be as specific as possible, knowing we might not be as familiar with your roads and cities. So it's important to reference nearby intersections, landmarks, or even latitude, longitude points to help us pinpoint where that weather is occurring, because that's also important for radar. Now, you can report through a variety of different means. You can either call us on the phone, you can follow us on Facebook or Twitter. We are trying to build up a little bit more our amateur radio operations and reporting methods. So you can also report to amateur radio. There's a special website for that. I can provide links for that if you need them. There's also a storm report page that we specifically have. If you don't want to interface with us on any of those means above, you can fill out this form on the storm report page, and that gets emailed to all of us here at the National Weather Service in Burlington. You can also use MPing, which is an app that the National Severe Storms Laboratory is conducting as part of an experiment, and you can send weather observations through the app. Or you can also share your photos with us as well. We would encourage that too. And so what MPing does, which I just mentioned, so this is an app you can use to submit severe weather reports with just a tap of your finger. It's a free app, and it uses the location services in it to kind of map out what your reports are. And so we can kind of look at these maps and say, hey, looks like people are reporting freezing rain farther north than we forecast. So we can adjust the forecast accordingly based on what we're seeing some of these reports as. All of these reports are completely anonymous. We do not know who or what. We just know a general vicinity of where reports are coming from. So you can give us an idea of when precipitation begins, if it's changing precipitation types, and of course you can tell us when it ends. So you can support research as a citizen scientist and report, again, as often as you like. So this is just a quick example of how to report freezing rain. So when you open your app, you can go in and select the report type. So this is me here at the office going in and saying, all right, if I wanted to report rain or snow, I would hit the rain or snow menu, and then it would open up each of the different kinds of rain or snow observations you have. And it's like, I want to pick freezing rain or ice pellets. And so once you select that, it'll take you back to the front page, and you can click Submit Report. And in that way, your report is, you'll send your report out. And you'll see that different regions of the U.S. will have, especially city areas, are going to be more frequent in their observation reports. So if that's something you'd be into, MPing is an option. Of course, it's always good to also have multiple ways of receiving reports. Just as it is to report to us, we encourage you to have multiple means with which to get weather alerts. Whether that be through the wireless emergency alert system, which is an automated system, depending on the type of warning we have. Not all warnings trigger it, but for specific conditions, this will go off when we think that, especially when the situation is urgent. Various weather apps might send you notifications as well. We don't specifically have an app, but mobile.weather.gov offers similar functionality, and you can bookmark that page for easy access. Text and email messaging services are also available with different sites. And then you can also follow us on social media, although I would recommend that not be your primary resource, especially in active weather. We might not be able to interface with you on social media at such a regular basis. So it's okay to have social media, but maybe not the primary one. And of course, you're going to have friends and family that can let you know as well. Be in communication with you, make sure you're okay and all that. Noaa Weather Radio is also a good resource to have. It's also good to have local news media outlets that you trust. Again, specifically, if you're especially not familiar with the geography, but you might know, hey, I know where this diner is, they're more likely to be able to reference local areas to help you know, especially where the most impactful weather is taking place. And of course, the Noaa Weather Radio. This is a good thing to have around, because again, if most communication networks are taken out, you can still have the backup of Noaa Weather Radio. We have different transmitters that transmit these very specific frequencies that reach your Noaa Weather Radio. And they have a host of other things, like we have our weather summaries for the area that also get sent out sometimes, especially for like the area around Lake Champlain. We also have the recreation forecasts that go out as well. So you'll get alerts for your specific area tied to the specific radio in that area. And if you ever need any help with that, feel free to reach out, and we are happy to assist getting your weather radio set up. All right, so we have reached now the end of the presentation. So I'll look out for any additional questions as we kind of run through the last segments here. So you might be asking yourself, all right, I've taken in all of this knowledge and would like to be a part of our spotter network. Remember, these are some of the things that we look for with what exactly to report. A tornado, a waterspout, or funnel cloud, anything that's spinning, good to know what's happening out there. Any severe thunderstorms, especially if they cause wind damage, heavy rain and flooding, or large hail, that's good to report. Any damaging winds like down tree limbs or structure damage is always good to know. Any lightning damage, or if there's been an injury, sometimes that's good information to know because we will write up reports based on that. Hail, specify the size, location, and time of occurrence. And of course, heavy rain, especially if it's over an inch an hour and happening over a period of at least 2 hours or more. Oftentimes when we get more than 2 inches of rain here, there are bound to be some kind of problems. And if you happen to see anything funny happening on the rivers or associated with ice jams, we appreciate spotting on that level. We have more advanced training on ice jam flooding. If you're more interested, I can always pass that along too. Heavy snow, always good to know, especially when you start getting significant amounts, greater than 6 inches or so, as well as snowfall rates over an inch an hour or even 2 inches an hour if the need be. With ice storms or freezing rain, especially if things aren't going quite to forecast or if damage is taking place, it's good to know what you're seeing there on the ground. So at the end of the day, a reliable Skywarn spotter provides ground truth and potentially life-saving information. We really do rely a lot on what our spotters are seeing, especially where the radar beam might be blocked or might not be able to see the lowest parts of the thunderstorm. So the spotter network is an important network, and we are happy to encourage you to seek out, maybe not seek out, but to actively report what you see, because sometimes just recognize, despite all of our tools, they have limitations. And so you can play a big part in helping patch up some of those limitations. We appreciate the efforts of our spotters. We have a series of regulars, and it's my hope, and recently we participated in Skywarn Recognition Day in December. It's ideally, when you do Skywarn Recognition Day, that first Saturday of December, you also designate a spotter of the year. I'm hoping to provide at least some recognition down the road for some of our most active spotters. We talked a lot about all kinds of different storms. We only really scratched the surface, but in general, the more organized, the more likely severe weather impacts are to take place. We talked about the differences between wall clouds and shelf clouds and overshooting tops and what kind of signals they might portend as far as weather is concerned. We talked about radar signatures and when severe weather is most common across this area, that being specifically July, but also June and August can be quite active as well. And then, of course, we can't stress enough that your safety comes first and that we never want you to put yourself in harm's way to provide information to us. When providing reports, it is valuable to be as specific as possible, just noting we might not be as familiar with your roads and cities. So landmarks and intersections go a long way into helping us out. All right, I see one question here, and it's a very good question. I'm happy to answer that. What are the thresholds for the different wind alerts for the North Country? I know we've had a few instances in the last few months and wasn't sure the specifics of wind advisories versus high wind warnings. Yes. So we didn't cover that in this presentation at all, but the wind advisory, specifically that's when you get wind gusts of at least, I'm not remembering the criteria off the top of my head, so I'm going to give me 1 second to remember the exact number. I think it's 46 miles per hour, but I'm going to get a specific number for you. All right, so when we're looking at a high wind warning, specifically, that's when we expect, so I guess the first thing to kind of note, when we issue wind advisories and high wind warnings, we call them non-convective. In other words, they're not associated with rain or thunderstorms. This is purely just from the weather patterns that are prevailing across the area that favor these particularly strong winds, even without a thunderstorm present. So a high wind warning is going to be 58 mile per hour gusts or greater, or it can even be sustained winds of 40 miles per hour or higher. The wind advisory specifically is going to be winds between gusts 46 to 57. So that number was correct. 46 to 57 miles per hour is the wind advisory. And so typically with that, sometimes you can get minor damage and utility impacts. Sometimes it even varies on the wind direction. And the high wind warnings is, you'll note that 58 miles per hour, that's the same cutoff for severe thunderstorm warnings. So those kind of cases aren't quite as common, but the wind advisory and the high wind warning kind of a separate category in and of itself. There's the other aspect of it that could also be, what are the different wind alerts? We talked a little bit about that there are different triggers for the wireless emergency alert system, and that depends on the wind speed that we put in the warning. If I were to quickly go all the way back to, we'll go back to this slide real quick. We went all the way back to our severe thunderstorm warnings and mentioned how we look for the winds of at least 58 miles per hour or greater. Well, what we can do, you'll see that we have the threat level of the wind associated in some of our graphics. And if we can actually increase this to say like 70, 80, I think even all the way up to 100. At a certain threshold, the threat level, we can hit a certain button that rates the threat as either considerable or catastrophic. That's probably not going to be too common here. But one of I think it's, I'm not going to speak off the top of my head. I'd have to review. I can get back to you on what the specific value is. But that can also trigger the wireless emergency alert for those high winds. Now, the wind advisory and the high wind warnings, those aren't going to push any of those wireless emergency alerts out. That won't ring on your phone. So answer the question within the question, perhaps, as well. All right. Excellent question. Very good one about winds, because they, again, don't have to be associated with the thunderstorm. All right. So let's move to the final review question. For those of you interested in becoming certified, when you report severe weather or any weather information, what information should you also include beyond the weather? If you said what happened, when it happened, where it happened, and of course what is your name and who you are, then you're correct. Sometimes it's also important to know how long it lasted, especially with hail and snow or heavy rainfall. This is also good information to know. Other than a ruler and a photo/video, any other measuring instruments that are helpful? As far as Skywarn spotting, that's probably all you need. If you are interested more in the co-op and CocoRa's kind of stuff, where you're more interested in reporting daily rainfall maps or rainfall totals that get brought into a larger network of weather observations, that's a little bit more of a special process. And if you have any additional questions, I am always happy to answer that after the meeting. All right. So I want to say thanks for your attendance and thanks for listening. I appreciate all the comments and the responses to the questions and that I've been seeing over the video. Appreciate your attendance here tonight and your attention. Again, if you are interested in becoming a certified Skywarn spotter and would like to be a part of our network of volunteer observers, email me the answers to the 10 review questions that we've had throughout the quiz, and that'll be the proof of attendance, since I may not necessarily know whether or not you've been here for the whole presentation. The good news is, since this is on a Facebook thing, this post will remain online following this event. So if you ever need to go back and refer to this, you can just return to the Facebook post and rewatch any parts that you need to watch later. If you need to email me any of your questions, responses, you can email me at robert.d.haynes@noaa.gov. Make sure you have the whole thing out there. Otherwise, there's another Robert Haynes out there in Noaa. So make sure you have that specific thing right. And of course, we have our different ways that you can access us. We have all kinds of different ways you can reach us for any of your questions. And feel free to let us know if there's any way we can assist you in any way. All right. We got about 5 minutes left on the clock, so I'm going to quickly go over some of this bonus slides. This is just to kind of outline some of how we kind of think of the different terrain features of Vermont, because we have, and of course Northern New York, can't forget them. We have just a wide variety of terrain. We're all these valleys sandwiched between mountain ranges. And that really makes our weather quite challenging both to observe and results in a lot of different microclimates across our area. It's a challenging area to forecast, to be sure. Especially cold hollows like Saranac Lake can often get 10 degrees colder than we have in the forecast. And sometimes we think, all right, I've accounted for the good old Saranac Lake cooling, and you think you've done enough, and they still blow it out of the water. Happens almost half the time, and then sometimes you think, oh, I've got it, and then it stays way too warm. So there's a wide variety of terrain features in our forecast area, a truly unique area of the world and a pleasure to forecast. We have the St. Lawrence Valley, the Adirondacks, the Champlain Valley, South and Central Vermont. For lack of a better term, we have the quote, Capital District, and of course, the Northeast Kingdom. And we've talked a little bit, we've hinted at the in the storm section that in July, oftentimes daytime heating overcomes the lack of fronts. Well, the reason why fronts are stronger in the winter months as opposed to the summer months is due to just the fact that the jet stream's stronger in winter. The thermal contrast between the tropics and the poles plays a big part in that. And the poles are going to get like into the 30, 40 below zero, whilst the tropics are going to almost consistently stay 80, 90 all the time. And so in the summer months, it's still about 80, 90, maybe 95 from time to time in the tropics. Whereas in the summer months, now you're closer to freezing here. So the thermal contrast isn't as great. And that results in a weaker jet stream, weaker fronts. But sometimes you can still get fronts from time to time with little streaks of the jet stream during the summer months. And this is just a chart of all the different storm types we talked about and the different hazards. And pretty much as you kind of go down the line, you get a little bit more likely for damaging winds, and same for hail, except tropical cyclones are a unique case because they deal with the freezing layer is so high up. You're very, very unlikely to get large hail out of a tropical cyclone, maybe in the far extent, the edges of it. And of course, flooding becomes a little more likely the further down the line you get, and tornadoes a little bit more likely. Of course, the supercell being the most likely to produce tornadoes out of all of these. So single cells, typically less threatening. Squall lines, supercells, and tropical cyclones, these are going to be typically your strongest kind of storms. We've talked a little bit about flooding, but really, if any of you are engineers out there, it's all about the balance of the system. If you have a lot of rain and snowmelt into the river that's outdoing the infiltration into the groundwaters or the natural stream flow, or not enough can evaporate, then all of a sudden you can get the river that overflows its banks. And of course, urbanization really plays a big part of that. When you straighten winding and curved paths and put a road that's a straight channel for water to flow down. So runoff really is most common in urban areas. And especially if the roadway happens to be made out of like an impermeable concrete or asphalt, and then water's just going to run straight down the river. So flooding can happen particularly in Burlington and Rutland. And then, of course, we discussed Barry's case of being almost a drainage between 3 different mountain ranges. So these areas, it takes less rainfall in these kind of areas to produce some of the flooding that might take a little bit more rainfall for less urban areas. And of course, with the ingredients, you want a slow-moving system with a high moisture content. Can keep thunderstorms going, even if you keep going over the same spot for a long period of time. And the most recent example of that happened last year in July of that happened a couple of years back in July. We had a thunderstorm complex that developed across eastern Vermont, and that kind of remained in the overnight hours. You can see even a little bit of an area of low pressure developed, and so it just eventually kind of kept these thunderstorms going along the Connecticut River Valley, and of course more storms developed and reached Barry, and so Barry had minor flooding that occurred from these thunderstorms that developed in the overnight hours of July 14th. We had a shout out to the Middlebury Tornado last year, a very rare tornado, probably the earliest in the record books that we've had. Tornadoes are possible at, I guess, now March through generally September or so for the most part. Whenever we receive tornado reports, we try and collect as much information as possible from reports. We try and map them out beforehand and match them to the radar signals that we see, just to get an idea of a plan before we go out and investigate and survey the damage that's happened. The enhanced Fujita scale is a really thorough roadmap that takes kind of the engineering and the structures of a building and helps kind of use that to estimate the wind speed. So it takes the damage indicators and assigns a wind speed value based on what you're seeing. And so using that, we can put all the lat long points of damaged buildings and uprooted trees, and we can take these damage indicators, and so we find them, we map them, and that can give you that's how we designate, like, this is how long the tornado was, and this is how wide it was, and this is whether it was an EF0 or an EF1. And so the tornado that touched down just east of Middlebury and went through a couple farms and structures had damage indicators of an EF1. And so based on that, and we had some damage along the ends of the path that were mostly EF0. So that's how we kind of map it together. All of this is quite important not just for the science of the matter, but also for the insurance world. It's important we get this stuff right. So we take this stuff seriously when we go out for storm surveys. And that's all I have here for tonight. And that's all the time we have this evening. But I will be around at least a little bit longer. I'll answer any additional questions in the comment section. And again, thanks everyone for your attention. Have a great night.